Good morning everyone and welcome to the NPTEL course Advanced Distribution System Analysis and Operation. Today we will start last module of our course, that is cyber physical layers in distribution systems. In this module we will cover few things related to the application of communication requirements in the distribution network operation, what are the process, mediums and cyber threats involved in it. Then as we know, no material or no medium is ideal. So, we will see what kind of non-idealities are there in the communication medium and how we can model them mathematically. And at last we will focus on cyber physical co-simulation framework and we will see some case studies with different kind of non-idealities in the communication network. So, okay. So, first we will start with the communication requirements in distribution network operation. So, why we need communication in distribution network or in smart grid at large? So, as per the Department of Energy, United States, the smart grid is defined that where you have multiple sources and multiple loads as well. Okay, that means source and loads both are there. So, how to communicate, like how you have to know as a control center, when you are sitting at the control center, you will come to know that how much is your load, or is your loads are responsive to the demand response program or demand side management or not. Even if you see at the distributed energy resources side as well, those are also very intermittent and uncertain in nature. So, you have to know at a certain interval how much it is generating, that according to it, let us say your solar panel is there, how much it is generating. If you do not know that, then you cannot command your storage to mitigate that uncertainty effect. So, because of that, you need, for automated energy delivery system, you need a two-way flow of electricity and information as well. Not only the electricity will become bidirectional in case of active networks, that is a smart grid or distribution network. Also the information has to flow from the load side to the source side and source side to the load side as well. So, allowing for near instantaneous balancing of supply and demand by leveraging distributed computing and communication technologies. Okay? So, communication in smart grid facilitates real time data exchange between distributed energy resources. You have DERs, you have smart meters at place in the customer side, then you have so many sensors, let us say SCADA sensors, or you have PMUs in the network. So, they are recording a huge number of data in real time, but that data is processed at the control center, that is not processed at the local level. Okay. So, that data has to be fetched or conveyed to the control center. So, that is done by your communication network, and that will enable automation, monitoring and efficient energy management in the distribution grid. Okay. So, with this process, when you do this kind of process, what you can do? We are enabling the protection purpose, like we can sense that what is the fault current, if there is any fault current, then how much is the fault current. Then according to it, we can enable or we can say the relays or the circuit breakers to act accordingly. So, protection, then control, then demand response and necessitating adaptive and resilient communication technologies that you need. Okay. But if you see at the normal communication system, like we talk in our phones or cellular networks, there is a difference between a normal communication technology and the communication technology adapted in the smart grid or distribution network. First thing, in this normal communication technology, what we do? We normally talk or we normally send messages, that is, there is a sender, a human being, and there is a receiver which is also a human being. Okay. So, depending upon that, your quality of service is actually the voice or the streaming, that means you are streaming some videos or audios. So, the quality of those, but that is ultimately done by a human. Okay. That is the main thing of the communication engineering, which is normally followed at the communication side. But if you come to the smart grid, there mainly we want automation or automated technology. That means it is a machine to machine communication. That means your DER controller, which is also a machine, it is talking with the supercomputer which is placed at the control center. So, that is also a machine. So, these two machines are talking together and no human intervention is there. Okay. And for that, that means there is a spontaneous, or you can say autonomous data exchange among smart meters, IEDs, sensors, actuators with minimal human interaction in case of smart grid communication. So, each smart grid application has distinct traffic characteristics such as latency, packet arrival, burst size, requiring flexible quality of service differentiation to handle coexisting functions like protection control. What does it mean? That means for in the communication architecture at the smart grid, all the communication lines or the communication infrastructure you installed, let us say you have a communication infrastructure between DERs and the control center, another communication infrastructure you have between smart meters and your control center, another you have with the PMUs and the control center, another you have with the SCADA and the control center. So, you have multiple communication infrastructure in place. So, the requirement of this communication infrastructure is not same everywhere. Somewhere you need a very highly time consuming, or let us say time dependent communication. That means if you send now a data that has to be reached at the control center within a few millisecond or microsecond time interval, you cannot afford a 1 second or 2 second delay there. Let us say we have seen in case of our protection that your backup protection and the primary protection, the difference between them is has to be more than a certain time limit, right? And also the fault must be cleared within a certain time limit as per the standards, right? So, how will you know if your data that a fault has occurred, that data is coming let us say after 5 seconds or after 10 seconds, then how can you be able to clear the fault within 2 second time? That you cannot do, right. So, if that is the case, so for every place depending upon the, you can say, necessary or depending upon the emergency of that equipment, depending upon that your latency, your arrival rate, that means your data rate or your bandwidth, that everything keeps on differing in the smart grid technology. So, smart grid deployments are limited mostly to revenue metering and non real time DSM, but utilities are planning for future applications that demand more robust and communication infrastructure. So, currently we have the communication in the metering structure, in the protection structure and the demand side management implementation, but that is increasing day by day. Utilities are focusing that each and everything must be automated, like we studied in the AI module as well, that the utilities or the distribution network operators, they are going to more and more automated kind of technology. Okay. So, selecting suitable communication technology is a critical challenge and requires a clear understanding of application specific requirements and comprehensive evaluation of available technologies, protocols and architecture. So, depending upon that, you have to know that which kind of topology or which kind of mediums you are allowed to install for a particular facility. If you are allowing, then what is the range of the latency is, you can say, allowed, or what is the range of the data rate you have to provide. So, those things you have to know to choose and to do a wise decision for choosing the communication technology. First, we will see that what are those quality of service parameters or QoS parameters, we call it in short, in power distribution communication. First thing is latency or delay. What does it mean? It means the time taken to convey a data from the source side to the destination side. Okay, that means sending a data from here and it is received at the other end. So, how much time it took from the to go from the sender side to the receiver side. For real time control and protection, it needs almost lesser than 10 millisecond. You can see for protection schemes, your data must reach to the receiver, that means it is the farthest end, let us say PMU, but the phasor and the magnitude that received data has to reach the control center within the 10 millisecond to inform about the protection or the fault condition. Then the second is the reliability, that is the probability that the data is delivered without errors. That means you are trying to send the data, if that is contaminated, okay, or it is, you can say, doped with some other kind of noise, or you can say erroneous value, then you cannot take a good decision from it. So, if your data is delivered without an error with a 100% confidence, then you can say your data, your communication network is 100% reliable, right. So, must be extremely high for grid stability and safety. When you have to ensure that your grid has to be stable, because stability, you cannot compromise with the stability, you cannot compromise with the safety, you can little bit compromise with the economics of the system, but you cannot compromise with the stability. If your system stability is spoiled, then that means your system will entirely go down out of order, right. So, then your reliability has to be greater than, you can see, 99.99%, that means it has to be 100% reliable. Then bandwidth, that is the maximum data transfer rate of the communication channel, that means from or through a communication channel, how much data you can send per unit time. That means if its bandwidth is very wide, that means you can say send huge amount of data. If you are using very narrow bandwidth system, that means you can send one or two data simultaneously. So, varies by application. For smart metering needs low bandwidth, and for DR coordination you need more, because smart metering means you are just taking one smart meter data. So, one communication channel you have till your control center. So, that bandwidth must not be very high. But if you go for DR coordination, then what does it mean? That means you, in the DR, you are sending more and more data, because every time the DR generation is changing. So, you have to send that data to the control center. So, you need higher bandwidth system. Then the fourth one, that is the availability, that is measure of system uptime and service accessibility. That means whether the communication infrastructure what we have installed, that is available or not. Most of the time communication is not dedicated, few only sectors have dedicated power networks have dedicated communication. Other than that, they are sharing with the common communication infrastructure. Okay. So, if that time whether your communication infrastructure is available, if it is available, then you can say that it is a continuous communication system. That means it is having 99.999% of availability level. Okay. Then jitter, that is the variability in packet arrival time. That means through a same communication channel and for the same distance, same receiver, same sender, sometime you are getting your data after 10 milliseconds, sometime you are getting your data by 5 milliseconds, sometime you are getting after 20 milliseconds. So, there is no certainty that if you send a data, within how much time you will get it. So, that uncertainty or that property is called the jitter of in the communication line. So, affects time sensitive operations such as synchronization and control loops. So, we have seen in our distributed OPF that the two area controllers, they are sending their data with together. So, that data exchange must be synchronized, that we have seen. But if your communication channel is having some jitters, that means one is sending in, let us say, 1 second time and another is sending after 5 second time. If that is happening, so what will happen? The synchronization will be spoiled and they will become unsynchronized. If that is the case, then your distributed OPF or any kind of synchronization operation will go out of order. Okay. Then your sixth one, that is the throughput. There is the actual data rate achieved over the network. That means you have designed for, let us say, 100 Mbps or 10 Mbps, but you are getting something low. If that is the case, so actually how much you are getting? You have designed for 5 kbps, but you are getting 2 kbps. That normally we experienced in our internet as well, that the maximum speed is something else and the actually available speed is something else. So, that is called the actual throughput, important for bulk data transfer like PMUs data. Okay. Then the scalability, ability to support increasing number of devices, important for future proofing and infrastructure. What does it mean? You have installed a communication infrastructure, but you know power networks are keeps on changing, more and more loads are adding, more and more DRs are adding, you are installing more and more PMUs. So, grid edge devices or sensing devices, they are keeps on increasing every month. Okay. but you cannot change your communication infrastructure every month. That means every month you are changing the medium, or you are changing your receiver or sender. That is not possible. So, you have to first design your communication infrastructure that it can take a certain allowable limit. It has certain allowable limits. If your power network is changed to up to a level, that much of data it can handle. So, that it says that how much scalable it is. That means you have designed for, let us say now, for 50,000 customers, but you can say your communication network can take till 1 lakh customers. That means that is your scalability. If it goes to 1 lakh 10,000, so at that time your communication infrastructure will not operate in the ideal manner. Then security, that is the most important. That means when you are sending a data, because every data is confidential, you are sending your customers data, how much they are consuming. So, if that is the data, so how much that is protected or it is exposed to the hackers. So, that will define that your communication infrastructure is secure or it is operating in insecure manner. Okay. So, for doing that, normally encryption, authentication and intrusion detections are normally followed in the communication structure. Then you have interoperability. That means, let us say you have multiple kinds of communication infrastructure, like you have Wi-Fi, you have wireless, you have wired communication, you have fiber, you have PLC, so many kinds of communication infrastructure you have. And also they are connected with different multiple kinds of your devices. So, how this seamless coordination is possible between these different communication mediums or protocols and also different devices who are sending data, right. That means your, let us say you have a smart home. So, that means the data will go from first from the appliance to the smart meter, then it will go from smart meter to the your, let us say aggregator at your locality, and then from aggregator to the main control center of the distribution network operator. So, everywhere you are using different kinds of communication protocols, that we will see, but how much they are interoperable. That means whether your appliance data, which is actually the main origin of the data, whether it is reaching to the control center without having any error or properly without having any delay, because every medium has their own latency and jitter and everything. So, whether it is sending properly or not. So, if that is the case, then we will define that it is an interoperable communication infrastructure. So, that is the QoS requirement for the distribution network application. Different cases you can see, if it is a SCADA, then latency must be very low, because SCADA data means it is used for stability, state estimation, this kind of purpose. Reliability must be very high, bandwidth is low, because the not very much data is sent. Jitters must be low, availability must be very high, and security must be very high. You can see the security must be very high for all the cases. Only demand response cases it is medium to high, but we are preferred always to keep it at the high level. Then if you say latency, then medium, very low latency is when you are doing distribution automation. Okay. That means when you need your system to be automatic, fast responding. So, at that time you cannot afford a single delay in your system, because everything is now connected. If one is delaying, that means other systems will also keeps on delaying, that is a cascading effect. So, at that time also you need a very low latency level. Then you have your DR coordination, that is also low. EV charging management needs medium latency, demand response needs medium latency, PMU needs very low latency, because that is the data you are using for protection purpose as well. Okay. So, that means it should reach within 5 millisecond, you can see, and fault detection it is ultra low. So, your protection devices, because you have to clear your data fault within 2 millisecond time. So, if your data is not reaching at the proper time, so even 4 millisecond is very high, your data has to reach within 1 millisecond time or 2 millisecond time. So, depending upon that, these are the other parameters or the range of the parameters of the QoS requirements of the distribution network applications. Now, how is the architecture of distribution grid communication network looks like? Okay. The first standard which came into the market by is IEEE 2030-2011 standard, which is widely adopted, and still we are working on this standard only, accepted for industry's first guideline regarding communication architecture and interoperability. Okay. What does it say? It says that there are three different kinds of architecture is present for the communication. First one is the private network, which is normally present at the communication at the customer level, like your home energy management, you are using some building energy management. So, it is a home area network or building area network or industrial area network, it is at the customer level, it is owned by the customer, like the internet connection you have at your home, like you have a router in your home, the outside connection is coming to that router and from that router you are connecting your all your devices. So, that is your home area network. So, that is present at the and completely your private network. What router you are using, what is the strength of the router. So, everything is dependent upon you, it is nothing to do with your service provider. So, that is why it is called private area network. Then you have neighborhood network, where all the data from the private network is accumulated and distribution network operator is mainly responsible to install that network. Okay. So, you can see that is at the distribution domain. Then you have the large or the wide area network, that is mostly connect your transmission grid, your generation side and your distribution side as well, which is actually that, let us say, market clearing, which is actually sending the data to your generator companies or the thermal power generators, that how much they have to generate or they need to ramp up or ramp down, all this data. Even for the transmission sector, you have PMUs, you have SCADA installation at the transmission grid. So, that data, that is a very huge, the distance of that wide area network is a huge few kilometers, let us say it is a system of almost 50 to 100 kilometers. So, there your communication infrastructure must be of 50 to 100 kilometers of radius and sometimes more than that. So, that is why it is called your wide area network, and that is connecting your generation and the transmission domain. So, your neighborhood area network, that is a distribution network, that is mainly is the connection between your wide area network and your private network. So, this is the overall architecture of the power distribution system with communication. You can see it starts with the home area network, that is your smart homes, where the devices are connected with their smart meter. Then multiple smart meters of different homes, their data are collected together and sent to the customer interface system through the local area network. So, LAN and neighborhood area network, these two are more or less same, these are owned by your distribution utility. Okay. Then this data, this is an aggregator kind of thing, you can see this is as an aggregator, like we have in our demand response or demand side management, who are takes the data and then send it to the DNO. So, then this data will be collated together, all the customers data, and that will be sent to your microgrid or your DNO controller, which does data collection, data configuration, pre-processing, management and analysis. Then two DNO controller, let us say they are nearby or let us say they are neighbors. So, they can talk with themselves with the wide area network, where the distance between them is large. So, generally they are done by wide area network. So, you can see here you have a connection, here you have Wi-Fi connection, here you have line connection or it means wired connection, and here also you have a wired connection. So, that is why we call it interoperability is very needed. You can see different kind of communication architecture, different kind of communication mediums are there. So, first we will see private communication network. What is the private communication network? It is divided into home area network, building area network and industrial area network, each serving residential, commercial and industrial environments respectively using wired or wireless technologies like Wi-Fi, PLC and Zigbee. So, what is the functionality and requirements? Hence, enable communication among smart meters, that I told that it is at the customer level. So, smart meters, appliances, HEMS, EVs and solar systems. These networks require low power because only small amount of data are always sent to the smart meter level, low data rates and must be scalable to support more devices. So, scalability is important for your home area network, because today you are having, let us say, 5 devices and tomorrow you are buying 1 or 2 more electrical devices. So, your network must be scalable enough, or that means be capable enough that it can accommodate those data as well when you install them. If it is not, then you have to change the entire communication as well, but that is not like favorable for from a customer side, right. Then energy optimization role, smart meters and HEMS in the hands can provide real time pricing and power consumption data to the end user. So, it is a two-way data communication that will send your load demand data to your network controller, and it will fetch the energy price data from the network controller and it will send it to the appliance or the customer level, helping shifting of load, that means your load shifting or demand side management, and reduce peak demand through informed energy use and decisions. Smart meters perform metering, power quality monitoring, and can control loads, act as an energy service interface with the home area networks. Then we will come to the next level, that is the neighborhood communication network. So, neighborhood area networks and field area networks, normally it is named as neighborhood or field or local, serve as intermediaries between the wide area network and the premise or the private area network that we have seen in the architecture. It is the connection between the wide area network and the lower level home area network, facilitating monitoring, control, demand response and distribution automation. NANs connect multiple customer premises to the utility control center through AMI system. That means all the smart meters data are taken together, then with the advanced metering infrastructure, you are sending the data to the control center. Okay. So, and with that data, the control centers are taking decision whether which data are flexible, which customers are very critical. So, which you can apply demand response, where you can apply your demand response, where you can do the demand distribution automation system. So, those things they take decision. So, these networks handle communication between numerous intelligent electronics devices and data concentrators or substations requiring high data rates, because you are sending huge amount of data, because most of the cases your number of customers are very huge. So, at that time you are sending together a huge number of data to the control center. So, your bandwidth of the system must be very high. Wide coverage, especially in the geographically dispersed area. So, if your customers are spreading with, let us say, when it is a very hilly area. So, at that time customers are not at a single place, that is, it is not a city. That means they are scattered into different places of the hills, but you have to collect all their data. So, that means your neighborhood area network must be capable enough or scalable enough that it can collect the data from all the geographically distributed customers. Infrastructure constraints due to existing grid setups and environmental variability, extensive infrastructure changes in NAN areas are often impractical. So, communication technology must be adaptable to different coverage requirements. That means, whenever you install a communication setup, that is even true for all kinds of communication system, when you install them, that has to be workable for, let us say, few decades. You cannot afford or you cannot change it multiple times in a year. Yeah, obviously you can upgrade a little bit. Let us say you are adding a new customer, so you are adding a new communication line from your control center to that smart meter, but it is not like that your entire communication structure is changed. That means, even at the NAN level, that is at even at the NAN level you are changing, let us say you have to change the medium because the data rate is not supportive. So, if that is the case, then at the plain or the cities, that is fine, that is doable. But if you go to very geographically, you can say, challenging area, very top hills, so there you cannot do these things multiple times. Technology mix, both wired and wireless technology like Zigbee, Wi-Fi, PLC and Ethernet are used depending on coverage needs and are expected to complement each other in supporting functions like DR integration. So, we have seen different kinds of technologies or different kinds of protocols are normally used for the entire communication infrastructure. Then the last one, that is the wide area communication. So, wide area communication is the backbone, that is the actual things where the SCADA, where the PMUs are connected. So, that is a communication backbone in the power grid linking the distributed elements like substations, SCADA system, RTUs, PMUs to utility control center. So, that is mainly responsible for keeping the system safety, keeping the system stability, everything should be keeping intact. That is mainly done by the wide area network, and obviously the data sent from the distribution side as well. So, that has to be very high speed and a very long distance communication. You can see the data rate must be in the range of GBps even. and it is a coverage of 10 to 100 kilometers. This is a two-way communication, enables two-way data flow, real-time measurements from the fields to the control center and control instructions back to the grid equipment. That means fetching the data from the PMU and then again sending the data to the relays to operate. Okay. Diverse technologies, common WAN technologies include fiber like optical fiber, power line communication, then cellular networks, WiMAX, and with satellite communication used for remote or backup links. Okay. So, this is the comparison between your WAN, NAN and SAN. You can see coverage area for WAN is 10 to 100 kilometers, NAN is 1 to 10 kilometers and HAN is only inside the home, that is less than 100 meters. So, primary role, that is the connect substation to the control center, it connects smart meters, field devices and data concentrators, and it is only the connection of the smart appliances present in the home. Data rate needed for the wide area network is very high, that is in the range of Mbps to Gbps. Your NAN is little bit medium, that is till 1 Mbps, and HAN is very low, that is 10 to 100 kbps. Okay. Then you have technologies used like PLC, that those are very fast communication technologies, that is mostly used for WAN. For NAN as well, we use PLC, Ethernet and ZigBee, and for HAN normally Wi-Fi or Bluetooth connection is done. Okay. Latency requirement is very low in case of WAN because there is a SCADA and the PMU data we are sending. Then for NAN it is moderate because tens and hundreds of milliseconds is possible, but for HAN that is not very stringent. You can have a lowered, or you can say a delayed communication medium is still acceptable for a private network. Okay. Then ownership is utility, and last one is the mostly customers, but also your utility can also, like if it is a direct load control, that means your utility has a direct control of your smart appliances. At that time even utility can install the communication system in your home. Okay. So, application, what are the application of distribution grid communication network? First, you can do it for AMI, that is the automation meter reading, demand response, substation automations, DR microgrid, electric vehicles, wide area measurements and distribution substation. Okay. So, what are, first we will see what is the automatic meter reading. So, that says as per the, there are three standards normally is followed for automatic meter reading, that is the ANSI C12.1, IEEE 1377 and IEC 619689. Okay. So, that says that focuses on communication syntax, and IEC standards offers to broader scope covering various AMRF functions such as meter data management, outage detection, prepaid metering. Which is normally does, it normally sends the meter reading, that is a advanced metering infrastructure. Meter reading, it takes the meter reading, it sends alarm, that means if something is bad meter reading or something, your meter reading has to be processed or it is not even recording something. So, that information it will send, it will even inform you about the grid events, that if something happened, let us say a fault happened at the upper grid, or let us say it is shut down, if something happened. So, that events will also be informed to the customers through this automatic meter reading and other kind of communication like your energy price and all these things will be communicated. Then how will you use demand response? So, real time data exchange, communication systems enable real time or near real time data exchange between the utilities and the consumers. That is highly needed whenever you are doing the demand response analysis. Then advanced demand response relies on two-way communication to send control signals from utilities and receive acknowledgements, consumption data or appliance status from users to the smart devices. Okay. Support for automation and control, communication network connect customer meters, thermostats and energy management systems, enabling automated load control without the need of human intervention, and that makes the more scalable and reliable. That means no human intervention is there, everything is automatic, you are getting the energy price, according to it that optimization problem is solved to minimize your electricity cost or energy bill, and then depending upon that it will decide which flexible loads must to be turned on, which flexible loads must to be turned off, and everything is automated. The customer also has not to be intervened, the utility also needs not to be intervened. It depends upon whatever the algorithms is fit for to the smart meters or the load controller for that demand response program. Then feedback and pricing signal, communication infrastructure delivers dynamic pricing, incentive based signals and feedback to the customers, encouraging behavioral changes and allowing informed energy use decisions during peak periods. That means it also say that okay, a high peak energy price is sent to the customers, that will inherently say the customer and load controller that now we have to reduce our load to minimize the electricity bill. So, the behavioral change, let us say at 6 to 9, that is your peak time, and at that time we are turning on our AC, but let us at that time your peak energy price is also at the peak. So, that will say okay, if you are turning AC, that is fine, but do not turn it on for the 3 hours, keep it for 1 hour. So, that will change the behavior of the customer. Then you have substation automation, obviously that is needed, because in the substation you have multiple relays, you have isolators, you have other devices which needs to be controlled or communicated properly. So, that is done by real time data exchange, enables fast and accurate transmission of the measurements, control commands and status updates between the intelligent electronic devices and RTUs. Fault detection and protection, so supports rapid relay coordination and protection functions. So, that means whenever you take data, your primary relay has to act in a very instant manner, and after some delay, if it is not operating, then backup relay, primary backup, secondary backup, everything has to be ready. So, that detection and the protection thing, like how fast you are detecting a fault, that we have seen in case of our fault one, that how we can use the algorithms. So, how fast that is responding, and that system is recognizing and then sending command to the concerned relays to operate. Okay? Minimizing the outage duration and equipment damage by triggering circuit breakers quickly during faults. So, you can see there are Ethernet switches, there are protection devices as well, and you have substation controller. So, at the station level you will process the data, you will send it to the bay level, and then you have the switches where actually that will be implemented. System monitoring and control facilitates remote monitoring and control of substation assets, improving the operational efficiency and reducing the manual intervention. Standardized interoperability ensures seamless integration and communication between multi-vendor devices using protocols like IEC 61850. So, you have in the substation there is not only one make, right, multiple devices are made by multiple vendors, multiple manufacturers. So, that has to be synchronized with a proper protocol. So, that is done by IEC 61850 standard. Then microgrid and DER control. You have the IEEE 1547.2 2008 standard provides specifications for interconnecting DERs, and the 1547.3 2008 provides the guidelines for monitoring, information exchange and the control of DERs. Real-time monitoring and control communication links allow operators to monitor DER output, voltage and frequency in real time and issue control signals for dispatch or curtailment as needed. Okay. Then it will ensure the grid stability and the integration by enabling timely data exchange, communication supports and grid services like voltage regulation and frequency support. Then remote access and the automation, communication infrastructure enables remote configuration. So, whether your DERs are at the very remote side, then also you need the data. So, you can see from this that DER controller is present for all the DERs, then point of load, and loads are also connected. So, everything must go to the DER, then DER will send that data through the PCC or the point of common coupling to the information exchange interface. There you have your electric power supply, that is your upper grid operator, you have your DER operator, you have DER aggregator and you have EDR maintainer. So, everyone has to be aware that how much your DER is generating or whether it is capable to take the loads or not. If it is not, then your AEPS operator or electric power system operator, so that has to now generate power or send power to your load for satisfying your load or the energy management system. So, again if this is the architecture for as per the IEC standard, this is the architecture as per IEEE standard. So, here the same thing is again done, that if you have circuit breakers, you have load circuit breakers and the DERs units as well. So, depending upon that your measurements, your battery system, your storage devices will act. So, that also says that interoperability and the coordination between different protocols, because you are using different kinds of protocols at different units. So, this even different standards you follow, right. So, substation follows one standard, your DERs follow one standard, your SCADA system follows one standard. So, if that is the case, so a seamless coordination between all those standardized equipment or standardized communication mediums has to be there. Then communication DER microgrids includes two main type of information. There is the energy management via neighborhood area network and monitoring and control via wide area network. Because of this shared infrastructure, strict quality of service control are essential to manage diverse traffic types with varying requirements and effectively. So, these are the data. You can see that utility operator sends the data that is conveyed to the DER controller, and then DER controller will send that data to the DER unit as per the IEEE standard. And then when the response is coming, DER unit is first respond to that system or to that request, that sends to the controller, then controller will send it to the operator, and then operator will take action and then send it to the utility operator. So, this is how the communication is there between unit, your controller, your operator, and then the upper grid operator. So, everything is connected through a communication medium. So, for electric vehicles the same thing, electric vehicles also and the charging controller, they has to be connected with the help of initialization, like when the electric vehicle must be connected, whether the vehicle is authorized or not, or there is any malware, that means it is not actually a vehicle, but a cyber attack happened. If that is the case, then there is authorization, then it has to respond against it. Then energy requirement is how much energy required, let us say SOC level of the battery, the charging, that whether that SOC level with that one customer is coming for charging or discharging, or what is the case if there is any falsified thing, or actually a customer is requesting from the far end that it needs a charging at your charging station. So, that authorization must to be done. Then the state of charge, how much state of charge is there, how much acknowledgement, and depending upon that your smart charging and billing management is done. Okay. That is through an application you are sending the nearest charging station that I want to visit your charging station for charging our electric vehicle and just book a slot for me. So, it has to know, your charging station has to know that whether that is a true customers or that is a malware. Okay. So, depending upon that whenever it is coming as well, so that charging also, like whether if it wants to participate in the vehicle to grid, if that is the case, then how much will be the billing, everything should be automated, and everything is possible when you have a good communication system in place. So, the communication infrastructure for EV charging involves home area network for home charging, neighborhood area network for the charging stations, and a wide area network when you want to add, because ultimately everything is connected with the grid. So, see the effect from that local level to the upper grid, you need the WAN connection. Then the wide area measurement, that is mostly needed, and that is using communication from the, you can say for last very like few years, that is for sending the synchrophraser data from the transmission, PMU data communication following the IEEE C 37.118/2005 standards, that will send the specifying a fixed 16-byte header and variable length of message body with the total data frame size depending on the reporting frequency and power system specification. Then you have low latency high reliability links you need, require communication networks often fiber optic and dedicated microwave with stringent latency and reliability to ensure real time relevance, requiring reliable communication and intelligent scheduling to avoid network congestion, minimize delays and maintain quality of service. Then distribution system supervision, that is you need for distributed monitoring scope, that means supervising the substation to cover passive infrastructure, overhead and underground lines. That means if there is any fault or any kind of problem is happening there, or thermal condition of the lines, that has to be aware to the substation level. Then multimedia and environmental sensing, that is the overhead line employs multimedia sensors for fault and vegetation. Okay. Then weather dependent renewables, that data also needs to be standard, and IEEE smart sensor framework, that will give you that to design the sensor, what is the standards you need for the transducer. And with that wireless interface via IEEE 1451.5 sensors, which says about the Bluetooth, Zigbee and other kinds of Wi-Fi or wireless mediums, that has to be again scalable and flexible, and your integration with wide area connection has to be possible, okay, for with specific requirements and deployment scenarios. This is the summary on the comparison table that you can see with the reference, with the traffic characteristics, with the critical aspects at each application level, what is the requirements for the communication medium. With this, I will end today's lecture and will continue with different kinds of communication mediums in our next lecture. Thank you.